Imagine a line, a simple, unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective, introduce a second line intersecting the first, and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one, and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past through the present and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place, but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time. thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the Flatlander example. In the 5th dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the 5th dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the 6th dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the 6th dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the 6th dimension could hop between these universes, learning the different outcomes and laws governing each reality. The 7th dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The 7th dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A 7-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the 8th dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the 9th dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the 9th dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the 9th dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline, and all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of the universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel. Concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M-theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. For years now, there's been a concept that defies the very laws of physics as we know them. A dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the Horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre Drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre Drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre Drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre Drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre Drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. Imagine a canvas of moments woven with the threads of time, matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas, film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light-speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes. Mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time?